Okay, topic 2.1 is electric field. So electric field is all about positive ion and negative ion. Now in the picture here we have a positive ion and there are lines around this positive ion. So what is it? Well, when we're drawing lines in this topic, it's usually we're representing the electric field, and this is called the electric field line. Well, why is it pointing away from the ion, you may ask? Because when we are drawing these electric field lines, we draw it as if there is another positive ion next to it. So in this case, when there is a positive ion, and we imagine there is another positive ion next to it, like over here, what will you do? We know that positive repels positive. So you go away, the positive ion will go away from this positive ion. And it's pointing in all four directions because that's how ions will react when they are placed in these areas. But you can draw as many lines as you want to, right? As long as the gap between them are equal, because we want to be representing this as like a uniform electric field. You can draw three, you can even draw two. I drew four because I like four. Okay, so Coulomb's law. Okay, Coulomb's law is used to calculate the electric force between two charges. So we could have a positive, that's terrible. We could have a positive charge over here, and we could have a negative charge over here. And they are separated by some distance. So how do we calculate the force that's acting between them, whether they're pushing away or attracting together? Well, there is that's why we have Coulomb's law. It's an equation. It's F equals Coulomb's constant times the charge of the charge of ion 1 and the charge of ion 2. And these charges are usually told in the question when you happen to do one of these Coulomb's law question. Charge 1, charge 2, they come together, and this is over r squared. So charge 1 times charge 2 over r squared. What's r? Well, the distance between them is r squared. So that's used to calculate the electric force between two charges. Next, we're going to do hollow conductors. So a hollow conductor, think of this as a metal ball, just a metal sphere. Inside it is hollow. Now this hollow metal conductor does not have electric field inside it. There's no electric field inside it. Well, why is that? We don't really need to get into that at this stage, but the short answer is that the inside has reached electrostatic equilibrium, but there are charges on the outside. And you could represent it if this was positive. It could be like this, 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 and the charges, the arrows pointing away, because if there was a positive ion next to this metal sphere, it would be repelled away. But there's no charge inside it, given that the inside is not charged. Well, when there's no charge there, it means there's also no electric field because we need charge to have electric field. So that's pretty simple. And also, I want to show you more examples of the field line. So we could have two plates. You know what? Two plates. Up here and down here. They're separated by a few centimeters. And the plate up here is positively charged, whereas the plate down here is negatively charged. So what's going to happen is, let's look at positive first, right? Positive. So we draw lines extending from the plate. 1, 2, 3, 4. You want to make sure the distance between them are same. So based on what we know already, the charges, the field lines are going to be pointing away. But what's going to happen to the electric field lines on the negative plate? Well, positive attracts negative, negative attracts positive. So quite conveniently, these lines just extend from the top plate to the, which is the positive plate to the negative plate. Because imagine if you place a positive ion here, it will just be repelled away by the positive plate, and then it will get attracted by the negative plate. But there can also be ones on the edge. So the ones on the edge are going to look something like this. So you could start from here, just quite awkwardly. Starting from here, it's going to make a curve because the electric field lines are always going to be 90 degrees to the plane that it originates from, that it touches. So since that is like horizontal, this is going to be vertical. But since this one comes off from an edge, it's going to start off kind of diagonally and then get attracted by the negative plate and end on the same like the same place. So the lines are still going to be the same like this, like that. So that's electric field line. And the next thing we have is corona discharge. Corona discharge, like corona, not a good thing, coronavirus. You know what corona is? So corona discharge usually happens with a conductor like this, like a water drop or a bird's beak, whatever. You know, like this, a bird's beak. Well, what is the electric field around this conductor going to look like? Well, we know that it's going to look quite evenly spaced out. You know, you have charge field line here and here, and the gap between them about the same. But in this case, this is not true because we have a pointy end and a not very pointy end. Charges are going to be accumulating near the pointing end. So we can have negative charges accumulating on this end, So the field lines around this area is going to be a lot greater. Well, if it's negatively charged, we better change the arrows. It's going to be like that. Okay. So we know that charges accumulate near pointy ends. So if you have a needle, the end of the needle is going to accumulate a lot of charge. So all these electric field lines are pointing toward the the metal conductor. You get the point, and they are even more concentrated at the tip of the conductor. So what does this have anything to do with corona discharge? Well, since the charges are more concentrated at the pointy end, the field strength is going to be stronger at these pointy ends. Now they're strong enough to polarize air molecules. That means to pull in this case, the positively charged ions in the air molecule towards it, and so that when it touches, it gains positive ions, thus ionizing the air. Now this air molecule, since it's since it's ionized by this conductor, is going to go on to ionize even more air. Now this effect, when you see it in real life, is called corona discharge, and it looks really cool. It's like you're making lightning, but with metal spheres or conductors, whatever. It's really cool. So that's how corona discharge works, because charge accumulate at pointy ends. That's it. 1.2 1 electric field. 1.2, 1? I don't know. Anyway, there you go.